So I welcome everybody to the workshop today. And my name is Albrecht Schmidt. I'm from LMU Munich in Germany. And this workshop is organized from people who are interested in the context of human-computer interaction in the Humane AI project. And I think some people may not be familiar with the project. That's why I talk a little bit about 2 or 3 minutes, and I mainly walk you through the website. There is more information on that later. And so the project is, I've got it here. The project is really a network project with 53 partners all around Europe, looking into what are the challenges that arise from artificial intelligence if we want to really harness its power for mankind, humankind, for us as humans. And I think we forgot to record, so I'm not sure who is.
I'm recording.
Are you recording already?
Yes.
Okay, so that's great. So I think that's one other announcement, that we are recording this meeting, but we're still very happy if you switch on your camera. So we like to see faces rather than black tiles. So if you have the bandwidth, we are really happy to see people, but we all completely understand if people couldn't go to the hairdresser for 3 months and rather have it off. So the project really wants to see how we can use AI, the power of AI, to make life better for people. And people in the work package that is concerned with human-computer interaction are really looking at this intersection. And it's not just intelligent user interface, it's very fundamental. What is fundamentally changing? And one of those fundamental things is human memory. So if you think humankind would not really work if we would have not long-term and short-term memory. And one of the things we came across in several discussions is once we change the way we live, and this has been done with writing some 1,000 years ago, we have changed how our memory works. Since writing, we remember things differently. And now with AI, we may fundamentally change human memory. And this is something we are interested about. And we think it's worthwhile to discuss this and to research this. And so looking at the relationship of human memory and AI, and also using human memory as an inspiration for AI, but also the impact the other way around. And this shows the broad challenges we see here. And before we move further, I show you sort of who is behind. Oops, that's Paul Lukowitz. He's one of the coordinators, and I wanted to go to partners, not to people. So if you look here, there are 53 institutions across Europe who are involved in the project. Have a closer look who is in there. There is the full list. And at this point, we have a lot of projects inside a project going on, like we call it micro project, that are going on. And hopefully within this years, we have a chance that we can get more and more people, also people who have not been joining the project from the beginning, into micro projects and to broaden the scope. So have a look who you find interesting on the map. There may be chances coming up also to really direct collaboration with funding from the EU later this year or beginning of next year. And I think one final part is this roadmap for research I want to share with you. So what you see a number of work packages that are in there. And what is really for the topic today, it is work package 3. It's human AI interaction and collaboration. And we cannot see this without looking at society and AI, and also at ethics and responsibility. And you see here, if you look at it, there are other areas like perception and modeling that also relates very closely to humans. and learning and reasoning. And then on the outer shell, we have quite a lot of application areas, domains, questions about creating enterprises, the socioeconomic impact, etc. So this is sort of a very broad range of topics we are going to cover. And with this, I'm at the end of the introduction, and I would give 1 minute to the co-organizers, each of them to introduce themselves. And we have greetings from Antti, who has a well-deserved holiday this week, and I have already seen him cross-country skiing, and I felt now with spring coming in Germany, sort of they still have a few really nice days for cross-country skiing. So he says his best regards. He may drop in on the mobile at some point, but I hope not. I hope he enjoys skiing. I think if there is holiday, I think we should really cherish that. So I think with this, I hand on to Alto for another person.
Okay, hi. I'm Kashyap from Aalto University. I'm a postdoctoral researcher here. I've been here for about 3 years now, and soon I'll be moving to a new position at Facebook Reality Labs in the Seattle area. My research work mainly is around adaptive user interfaces, intelligent user interfaces, and also computational methods for designing things like websites or GUI layouts. And that's mainly where my research interest in this project also comes in, because it also combines these aspects of intelligent UIs and AI together with aspects such as memory that can drastically affect or impact how adaptive UIs, for example, work. And it's great to see all of you here in large numbers.
And we move on to a similar building in the background than I have. That's Munich.
So, hi, my name is Robin Welsch, and I'm a postdoctoral researcher with Albrecht Schmidt at the LMU Munich. My research revolves around how personality works in virtual reality, and therefore also how memories impact virtual encounters. And there, obviously, AI plays a role in this personality and virtual domain.
Okay, I think with this we are right on time to start our program, and we are really excited to have Zoya with us for a keynote. I think for her it is really early this morning. I'm not sure how early it is, but you look really fresh, so I was surprised. So you had to get up early, but we are really excited that you take the time to talk to us and to give the chance for discussions. And here you can see on my screen the rest of the program. We have different talks, and in the panel, this will be more like getting all the discussion from the talks together and hopefully involving as many of you from the audience to push this forward. And the hope is really that this is inspiring, creating new ideas for research collaborations, potentially new micro projects with internal and external partners to really move the field forward. And without any further ado, welcome our keynote speaker, and I think we can clap. I have the microphone open, and I think the others can clap visually. So welcome, and I stop my screen sharing, and you can share your screen, please.
Sounds good. Do you see my screen now?
Yes, perfect.
Perfect.
And you hear me? Yep. Okay. So thanks a lot for the invitation. My name is Zoya Bylinskii. I'm a researcher at Adobe. So I'm in the Cambridge, Massachusetts lab in the US. And actually, most of my talk today will be based on the work of myself and others in the lab of Oertel during my stay at MIT. And so in comparison, my work at Adobe in the last 2 years has focused mostly on attention and saliency models. Let me make sure I can switch. There we go. and graphic design applications, which I'm happy to talk about offline. But I do have the expectation that memorability will creep back into my research any day now. So this work that has been done at MIT on memorability, it's soon to be summarized in a book chapter in a Springer book on the human perception of visual information, psychological and computational perspectives, with a great group of editors. There, we're going to provide a comprehensive survey of computational image memorability models and the applications to date. So if you're eager to lay eyes on it earlier, please do send me an email and I'll send you a preprint. So now I just want you to recall the flashing images from my title page. I hope you remember seeing this image, maybe this one. What about this one? Nope, you didn't see it, I promise. And motivated by this demo, what I'm going to talk to you about today is the memorability of images. So this is a concept that was pioneered in Dr. Oertel's lab at MIT. And here, we're not focusing on the observer. We define image memorability as an objective and quantifiable measure of images that's mostly independent of the observer. So we'll come back to question that later. But the idea is, and our working hypothesis in the group, is that this measure of image memorability that can be extracted from the image pixels alone captures the utility of information. You remember what is going to be useful to you. And in application form, we can use it as a filter for visual data. So more broadly, if we consider what are the applications that can be enabled, if we have a better understanding of, well, memory generally, but also image memorability and something that we can compute, we can use it to understand normal and abnormal human function, diagnose problems, and maybe even general biases and memory mistakes that we make. We can also use it for better design of whether it's of mnemonic aids or user interfaces or logos, educational material, visualizations. So I'll talk a bit about visualizations later in my talk. And you know, we could think about the fun and cultural applications. Can we use memorability to understand why certain things stick in our cultural memories? So I'm just going to give you a brief experimental rundown for those who aren't familiar with our experimental design. We've been running this design since 2011. The idea is to study memory using a game, and this is crowdsourced on the web, on Amazon's Mechanical Turk, typically. So much like what I did to you at the very beginning, where I flashed a series of images during my title slide, participants see a sequence of images, and when images repeat, they're asked to respond. And so based on that, memorability is just the fraction of people that correctly remember seeing the image in this sequence repeating. So given those responses, we can then measure consistency of a population. How consistent are people at remembering and forgetting the same images? So to do this, we take our population, we split it in half, we rank the images according to the memorability scores of one group of participants, another group, rank correlate this, and then average this value over many random splits of participant data. And just as a reminder, correlation is measured, this is Spearman correlation from -1 to 1. And what you can see in the middle column here is the correlation values that we get, the consistency between participants for all sorts of different memorability studies that have been run from 2011 up until a study last year on video memorability. And we see that these correlation values are in these high 60s, 70s, in some cases 80s. So this is remarkable consistency, independent almost of image type. So you can see on the right that these different memorability data sets capture different kinds of stimuli. We have photographs, faces, visualizations, natural scenes, man-made scenes, diverse photography. And in all cases, people tend to remember and forget the same images. This is a pattern that comes up again and again and has been validated. So where does that leave us? If indeed the same set of images are generally memorable and forgettable across a population, we can factor the observer out of the equation for now and treat memorability as an intrinsic property of images that we're going to extract from the image pixels. That means that we can computationally predict it. And so this has sparked then a whole line of research to build computational models to predict image memorability. So this includes the work of Aditya Khosla from our lab, who both introduced the largest image memorability data set to date. So this is LaMem, and that's served as training and evaluation data for many memorability models since then. So there's 10,000 images with memorability scores collected using our memory game. And he also introduced one of the first deep learning based memorability models. So aside from just predicting the memorability score of the image, as you can see here at the bottom, it also predicts a memorability heat map, which visualizes the image regions that the model predicts contribute most to memorability of this image. So here's another slightly different visualization of the same. This shows the image regions that are most positively correlated with memorability at the top. So faces, body parts, tangible objects, objects we can interact with, stick in our memories. While image regions correlated with low memorability, they include broad swaths of sky, sea, fields. In general, we find across study and study again that landscapes, even aesthetic landscapes, beautiful landscapes, they're very poorly encoded in memory. We tend to compress them, false alarm on them a lot. They all look similar to us. They fit this kind of prototype in our brains. Now, follow-up computational work since 2011 has consistently improved the models that predict memorability from the image pixels. These models have gotten more complicated. They've used higher level features. So for instance, this is a model from 2018, which is also a deep network that includes an attention module, and it iteratively refines its predictions. It's kind of glancing at different parts of the image and refining how memorable it thinks this image is. And then it outputs the final memorability score automatically computed. And this model in 2018, this is kind of the last of a sequence of models. It comes closest to human ground truth. So if we look at the inter-participant consistency that I told you about earlier, that's at the top here across 3 different data sets. So you can see that LaMem was at 0.68. Then MemBoost is just there, right around there. And it's coming close to for some of the other data sets as well. And this is a boosting model on top of a deep neural network. So, you know, if we kind of stop here, then I can claim that memorability is solved and end my talk early. But I have given multiple talks on memorability in the past, so I can predict what your questions are going to be. And what I'm going to do with the rest of my talk is spend some time answering them. So let's start with questioning how stable memorability is across contexts. What if you change the context in which an image occurs, the sequence of images that you expose along with it? Well, in order to dive into this question, back in 2015, I curated a data set of scene images that span different indoor and outdoor scene categories with hundreds of images per category. And then I ran different sets of memory experiments. So in one case, an image is presented in the context of images from the same scene category. So for instance, a bathroom image among other bathroom images only. And then in a separate set of experiments, I mixed all the images from all the categories together. So critically, I now have memorability scores for an image within context and across context. Now, if we just look at the results, what's interesting is that even at the individual category level, we see remarkable consistency across participants. So until this study, we thought that some of the memorability consistency can be explained away by categories. Maybe everyone tends to remember indoor scenes and then forget outdoor scenes. I told you that is a trend in the data. But even if you look within category and you run experiments on individual categories, so just pasture images, for instance, you're still going to find remarkable consistency across people and what they remember and forget. They're still going to be the most memorable images and the most forgettable images, with a large spread of scores in between. So what does make an image within a particular category memorable? So if we just qualitatively look at the data, memorable instances tend to have unusual objects, layouts, perspectives, and colors. You can see some examples of those on the left of the screen in comparison to some of the more forgettable images from the same categories on the right of the screen. So you can see, amusement parks and houses and airport terminals and cockpits. Now, this isn't surprising that the most distinct images are more memorable. We've known this for a while. There's a large body of memory literature that suggests that distinct or unique items are better remembered. But our goal with this project was to automatically quantify this intuition using a large set of natural scene images, which wasn't done before. So we turned to information theory, and the goal was to quantify the distinctiveness of an image as its negative log likelihood under the other images in its context. So if it's very different from the other images in its context, we want to predict that it's going to be memorable. And so the way we computed this is we took all the images in an image's context, so all the other images that it would be shown along with, we computed features, and we tried anything from low-level to high-level features. It turns out that high-level features from a deep net work best. They capture these higher level semantics, kind of object categories that's a better predictor of memorability. And then once we have those features for all the images, we can compute a probability distribution over them. We use a Gaussian mixture model. And then any one image, we can estimate its distinctiveness as its negative log likelihood under this distribution. So to give you an example, let's look at the bridge images on the left side of the screen. So these images of bridges ended up being very memorable when only considered in the context of other bridge images. And if you squint at them, you realize that they don't look as much like bridge images as other categories. They look like pastures and mountains and seascapes. That's what makes them stand out. And for the exact same reason, when these images were combined with images of other categories, they drop drastically in memorability, because now you're confusing them. You're collapsing them in memory with all the other scene images you're seeing. And in contrast, if we look at the images of bridges on the right here, we see that these are the memorable bridges. Not only do they not look like other scene categories, so they're going to stand out as bridge images, even among the bridge images, they're unusual. They have unusual structures or colors or setups or objects. And so the takeaways here is, if you want to make an image robustly memorable, you have to consider the context in which it's likely to occur. And you want to make this image distinct with respect to each of the contexts in which it's going to occur. That could be difficult, but you can keep that in mind and try to optimize for that. Now, if we look more broadly across the whole context, across a whole scene category, we also find that across a population, some scene categories are intrinsically more memorable than others. And I alluded to this before. So for instance, amusement parks are intrinsically more memorable as a category than airplane cockpits. And on average, the images in those categories are more variable. So let's quantify that intuition as well. If the distinctiveness of an image was defined as its negative log likelihood, then the entropy of a whole category, the diversity of the images, can be captured as the average negative log likelihood of all the images. So let's take a look at this plot where memorability, average memorability of a category, is plotted against this entropy measure. And we can see in the rightmost of the plot, in the right corner, a category with high average memorability, amusement parks, and high entropy. And you can see the images on the right-hand side. Different images of amusement parks capture different vantage points and different combinations of objects. Whereas a category like cockpits in the left here, you can see that it's pretty much the same scene over and over again, same vantage point. It has low entropy, so low variability of visual features, and it's also the least memorable category. With a caveat that this is for the average observer. So here I am glossing over specialist populations such as pilots, and we might go back to this later. So say you want to apply this. How can you? Well, let's say you want to make your content more memorable. Within a given sitting, you want to increase the amount of information that can reach your viewer. You want them to remember more of the content that you present. Well, the goal is increase the diversity of the content. Don't have a stream of identical looking images. Instead, you really want to shake it up a little once in a while. So with that, let's move on to the next question. How stable is memorability across time? So original work from Philip Isola from our lab in 2013 showed early on the remarkable stability of memorability ranks across time. So that means that images that were highly memorable at brief delays were more likely to be highly memorable at longer delays. So an image that repeated after a lag of only 15 images, remember images are repeating in a sequence, so 15 images later is just over 30 seconds. Those images were, how memorable they were at that short lag was already predictable of how those images would fare across longer time spans. So our work then built on that and went on to show that differences in memorability across images show up even earlier than we thought. Already after 20 seconds, we see differences in image categories. So here you can see the lowest, medium, and highest memorability images colored with these lines, red, blue, and green. And you can see that there's already a gap at low lags in terms of the difference in memorability scores, but also in terms of people's response times. So they're already slower at remembering those images if they're low memorability. Moreover, those differences increase over time. So a forgettable image will fall off in memory at a greater rate. And this finding was recently replicated in the domain of videos as well. So here, video memorability ranks are also preserved over time, as you can see. So the most memorable image is this yellow line, and then every colored line is a different video. And just like with the images, we see that there's also a different decay rate. So the most forgettable images are forgotten at a higher rate. So if you ask people much later, they're going to be more likely to forget it. And this work on video memorability came with a model. So this was just recently, it came out of the Oertel lab as well. It was presented in ECCV in 2020, a computer vision conference. And there they present this video memorability model that predicts not just the memorability score for the video, but also the rate of decay. So you can predict how memorable an image will be at different points in time, maybe 40 minutes later, for instance. We're not talking about really long-term memory of multiple days, although there's some work in this space as well. And it also shows stability of ranks. And so far, kind of all this work that I've presented and overviewed for you, it's completely ignored any of the individual factors. And I told you I tried to go back to this. So here, our goal is, instead of attempting to predict image and video memorability at the population level, averaging over observers, for application purposes specifically, we might want to make memory predictions for a given individual on a given trial. So what does that problem look like? So say we're exposing the individual to a sequence of images. It could be images or visualizations. We might want to predict whether that individual looking at that image will be likely to remember that image later on. We can build applications on top of it. Now, if indeed what I told you is true, that people are consistent with each other, I should be able to predict the memorability of the individual, let's say Bob, with the memorability of the population. So when Bob is shown this image of a kitchen for the first time, will he remember seeing it later? If the crowd remembered seeing this image, I'm going to predict Bob will remember seeing it, and vice versa. If the crowd forgot this image, so will Bob. And as a baseline, this population predictor does quite well, expectedly. So it's well above chance. And this is particularly because people are consistent. But what happens if we remove images from the extremes? If we're removing the images that are most memorable and forgettable about across a population, we're removing the images that people are consistent on. And when we enter the space of images that are half the time memorable and half the time forgettable, depending on the population, so they have like this 50% memorability rate on the extremes, well, you can't use the population to predict the individual anymore, because which bucket you're in, you're remembering the image or you're forgetting the image, depends on you as the individual. So here's where we're going to target those individual features. And in my work specifically, I looked at the attention of the observer, so of Bob, in order to predict whether Bob will remember the image. I'm going to look at eye tracking. And very, very coarsely, the idea behind our model is that if you look at regions of the image that are distinct to that image, we're going to predict that you're going to remember the image later. And that is kind of visualized in this middle panel here. So what you're looking at, each row is an image, and each of the little squares is individual observer and their eye movement patterns on the image. So in the middle panel, our automatic model that looks at eye movements, and at that point it was a simple classifier trained on these fixation maps. Our model predicts that all the people in the middle column will remember these images because of how they looked at them. You see that they're kind of paying attention to individual objects scattered around. Whereas all the people on the rightmost of the screen here, our model predicts they're going to forget the image. And the color coding shows cases where our model makes a mistake. So it's not all in the eye movements. Failures can occur during, this is encoding predictions. Failures can occur during recognition, or because someone's not paying attention to the task in general, even if they're looking at the images. But in general, this model did quite well. So if we compare it to our population predictor, we have a nice jump from 60 to 66%. This was statistically significant. But the most important point is that this holds across all images. So this is a stable predictor. Images that a population wouldn't help you predict the memorability of an individual on, the individual features, in this case, this person's eye movements, do. And just as a sidestep, we also showed that pupillometry gives us a clue into memorability, into an individual's memory. So here we borrow ideas from the cognitive load literature. And so for those of you familiar with it, it tells us that high cognitive effort is often associated with larger pupil dilations, because you want to take in more of the visual world, and reduced blink rates for the same reason. You're taking in more of the visual world when you're cognitively loaded. So let's consider these three classes of images, those with high, medium, and low memorability, color-coded as green, blue, and red. So what we find is that at retrieval, so when it's time to figure out whether you've seen an image again, we already see significant differences in pupil dilations and blink rates. So as you can see from this bar graph on the left, the pupils for the low memorability images expand much more. So we're already seeing that people are having a hard time to retrieve them from memory, and pupils are much smaller for easily memorable images. And similarly on the right, we see a reduced blink rate for the low memorability images. People are really struggling to retrieve them from memory, and a kind of more normal blink rate for the high memorable images. So to summarize this part, I just want to leave you with this notion that the eyes can give away clues about personalized memorability, and we can imagine using them in cool applications in the future. And in my opinion, this is perhaps the most exciting area for future investigation, since the predictions that I've shown you so far, the 60-66% level, they're not yet accurate or robust enough for use in real applications. We are seeing this significant signal, but if you want to deploy this in the wild, you really need to boost this accuracy. And there's more work that's come out since that about tracking eye movements using webcams or using cell phone cameras. So maybe that can be integrated together. I think in general, this is a very exciting space. Now, moving on to our last question. How stable is memorability across image types? I how generalizable are the findings there? Well, I alluded to this early on. So I showed you this table of image memorability and even video memorability down at the bottom, data sets, and how all of these studies have shown that content is intrinsically memorable. We've seen high human consistency in all these different data sets. But what we're going to do now is dive into a couple of them. My own work, and this is from 2013, tackled the domain of visualizations. And the goal was to bring us a step closer to educational applications, something that's not purely visual, but maybe has some information content as well. And for this effort, we curated a collection of diverse visualizations. And much like with natural scene images, we categorized the images using a taxonomy, and we annotated properties in the images. So as you might want to annotate the objects in natural images, we annotated the features of visualizations: colorfulness, visual density, the presence of pictograms. And this was all in order to make analyses of memorability and how these various attributes affect it. We used very much the same experimental paradigm as with natural images. So this sequence of flashing images with visualizations. And again, we found high consistency across the population. Some visualizations were indeed consistently more memorable than others. And in paralleling our findings with natural images from before, what makes a visualization memorable is if it's more distinct. And in the case of a visualization, it can be distinct in terms of those relevant visualization feature axes: how colorful it is, its visual density, its presence of pictograms, etc. And paralleling our finding on context entropy, memorability also varies across publication type. So those venues that have more diverse visualizations overall are also more memorable on average. People remember more of the images from those publication types. And finally, having human recognizable objects makes visualizations more tangible to observers and thus more memorable overall. So I think this is the utility of information kicking in here. Now, importantly, in follow-up work, rather than just flashing a series of visualizations for short periods of time, we also collected data on showing those visualizations for longer periods of time, so people have time to read and explore the visualization in more detail. We collected eye movements, and we collected textual descriptions from memory. And that way we could relate those additional measurements to memorability. I'm not going to go into the details here. We can get into it with questions, but the takeaway was that if a visualization was memorable at a glance, it was also more likely to be encoded with details. So not only would you remember having seen this visualization before, but you could more accurately, in some cases, tell me what was the content of that visualization or what was plotted. Switching gears a little, other than visualizations, other work from our lab has extended the study of memorability to faces, again, correlating different domain-specific attributes to memorability scores. Now, my personal takeaway from these findings, also in line with this previous work on scenes and visualizations, is that the most aesthetic, the beautiful faces, they're not any more memorable, but the untrustworthy ones are. And I think that this again points to this utility of information. What is the face that's worth remembering in the future? Follow-up work on this face memorability and this data set that was presented took this a step further, parametrized the key points on the face image and used a computational model to warp the face image. And this model could predictably make images more or less memorable, which was very exciting. And this was back in 2013. And in 2019, in a computer vision conference, this notion of modifying memorability has been extended to arbitrary images. And this time, instead of some parametric key point models, this particular work, also from the Oliva lab, it leveraged a state-of-the-art GAN. So for those not familiar with them, generative adversarial network, creates an image from a kind of a noise feature vector. So given this a seed image within the GAN's within the GANs topology, the model could transform that image to be more or less memorable. And so if you look at these images, you can see that as the model zooms in on the subject matter, centers it better within the photograph, removes the clutter, makes it more orderly, the memorability of the photograph also predictively improves. And this is measured both by a computational model of memorability and by human observers. The current limitation of this work, however, before you get excited and you try to apply it to your own images, is that this particular model can only modify the memorability of images that are already in the GANs manifold. So you're not going to be able to upload your own image. But there's new developments in GANs that will allow you to map an arbitrary image into GAN space. So basically, there's still a lot of space for exploration here. And fully automatic models that can take an arbitrary image and modify its memorability, they're close, but they're not quite here yet. So with that, let's look into the future. And what I think it holds for us is the ability to capture continuous streams of images and have smarter, perhaps more memorability-based models that will compress and filter the content to present to us again. And I think that learning how to do this on a personalized level, where we take into account the individual characteristics like attention or preference or context, they'll be particularly important. And they'll be particularly important in the case of specialized populations. So I mentioned that most of my talk glossed over the target population. We did talk about high consistency across a population of participants, but the disclaimer is that most of the studies we ran are on crowd workers in the US. So this work has yet to be expanded to study how memorability behaves in other cultures, in other settings, and where the target population might have specialized knowledge. So I'm sure, for instance, that not all cockpits look the same to pilots. They have special meaning attributed to them. And finally, I think that memorability can also be used as a feature to optimize for in applications like tourism and navigation. How about picking the most memorable path? And I'm just going to conclude the talk with a message to the early career researchers among you. The most memorable path is the path least traveled. And memorability is distinctiveness. So I wish that you can pick a distinct path and enjoy a memorable career. I'll stop there. Thank you.
Thank you so much. And so we're really happy that you took the time to come, and I think this is really exciting work. And we have a few minutes for questions, so I think we have sort of this buffer at the end, so it will not go longer. So I think I start with a question while you can think of questions, and please put them in the chat, and then we can unmute you. So I think picking up on the final part you had, I think, so we did some work where we primed people with things in real world situations. So it is very rarely that people are not sort of going with a task. So I think a crowd worker has a very simple task, remember this, but usually we go through the forest collecting mushrooms, and we see the mushrooms, but don't see the butterflies. And if we are told to take pictures of butterflies, we will not see the mushrooms. So I think this question about priming, do you have any idea how we could study this and how we can use it to improve, sort of get beyond the 60%, that we really get to a point where we can use it in applications?
So there's a few questions packed in there. So let me try to answer them a few different ways. There has been work that's taken a look at people's attention as they look at images, that's trying to predict the attention maps and figure out which specific parts of the image are going to be remembered. So they disregard the memorability of the whole image. They care about what content in that image is going to be more memorable. So there's some exciting work in that space. So if you're searching for mushrooms, you indeed will ignore everything else, but we will see that in the data, because if we show the image to you again, or we show you parts of the image, we show you just the mushrooms or just the butterflies, we can measure that indeed you remember having seen the mushrooms before, and maybe you don't remember seeing the butterflies. So you can disentangle the context. You can show those parts separately. So that's given us a way to examine what different people focus in on and test the memorability of individual objects. In terms of your question about how to use individualized attention and improve our prediction of whether someone's going to remember something, I think one aspect is the work that I presented on context modeling is a separate work than the one that used eye movements. So if you combine the two together, if you know what are the other images, or it doesn't have to be images, events in the individual's recent past, but also over their life. I imagine that if you grew up in a very different world, what's relevant to you is very different. And perhaps if we have snapshots of your life, if you're wearing, Internet of Things and you're capturing it constantly, we'd be able to model it. We'd be able to pick up on signals that look different from the norm for you. And I think that would improve our individualized predictions. Also, at the time that I had done the eye tracking based memorability prediction model, we had much simpler models. Right? This was an SVM based model. Since then, there's a lot better models that can take eye movements and predict observer task or task difficulty or some other features. There's some work in computer vision that shows that where you look on a website can predict what task you're trying to do on that website, and pretty reliably. So that's already being used in applications. It's not being used to predict individual memories, but it can. So that's kind of a low-hanging fruit, I think. And I think we'll get way past the 60% we were seeing before with simpler models.
Thank you. I think Patrick has put a question in. Do you want to raise it directly on the microphone?
Hi, thanks for this very interesting talk. I was wondering whether you investigated the possible influence of the scale of the scene with respect to the scale of the human body. Thank you.
That's a good question. Me personally not, but our lab did. And the interesting finding is that what you find most memorable is the content and the images that contain the content that you could interact with more. So that work showed, and it was more in the neuroscience context, that if there's objects that you could interact with, like hand-scaled objects, you almost have a different you do have a different neural pathway that processes those objects than processing objects that are beyond body scale. They're somehow more abstract to you. You don't hook onto them. And so indeed, we see this in our general image memorability work, that indoor scenes or scenes that contain objects, close-up objects, they're the most memorable. And as we step away and we look at vaster expanses and larger spaces where we can't quite configure our bodies, right? It's some distant mountain scene. Those are the most forgettable. So indeed, that's related, and those are two different pathways in the brain that process, and potentially there's evolutionary reasons for that. You want to process much quicker things that you're likely to interact with than these more abstract environments that you might have to navigate through. And I will say that somewhere in between there, between the objects and these natural distant scenes, are the indoor scenes through which you can move your body. But those indoor scenes are less memorable than scenes containing close-up objects. Thanks for your question.
Okay, so we have more questions coming in, and I think we just take one, and I hope you're still later there in the panel, so we will take Kunal's there, if this is okay for you later in the
panel. Yeah.
Okay, so then we, Soo-young, do you want to raise your question also on the speaker, or should we read it out?
I can speak it out. This just reminded me a lot of the von Westropp effect that's been studied in psychology. And I was wondering if you had made a connection between memorability and that. And usually it tends to be explained by a change in attention, but I don't know if you have a take on that.
I had a very hard time understanding the audio. I don't know if Albrecht, if you did, or if you could pull up the question.
I read it out, and then I think we'll probably can make sense of it, because I had also trouble hearing the audio. This seems like a model of the von Westropp effect. I'm not sure if there are other models of this.
I'm not familiar with that effect, but I'm happy to kind of look it up and then maybe in the panel provide you an answer.
Okay, and I think this is also a good chance for following up. So I think this is sort of, I think perhaps we can pick this up later. And also I think Kunal has a question that's also probably a much broader question about sort of the question about emotion and images. And I would like to have this in the panel. So Kunal, could you make sure that we don't forget it later, that you keep it and come back with it? And there's also in the chat about the Restroff effect. So perhaps we can put it later, or I think there's always a chance to follow up on the discussion. And I think with this, we thank you again for the talk and looking forward to more discussion. So thank you.
Thank you.
And we move with a slight delay, but we'll pick up on speed to James. James, you want to share your screen, and we go straight into your talk. And perhaps you introduce yourself with just 2 or 3 words to make it not to make it short, that we know who you are and what you're working on.
Right. Thanks, Albrecht. I'm James Crowley. I'm professor at Grenoble Institute Polytechnique at the University of Grenoble, researcher at INRIA, and actually coordinating work package 2 of Humani.net. So I'm going to talk today about a recent doctoral thesis by Thomas Goots of my group. Was defended in September. This is work that was really done in collaboration with Professor Thomas Schack at CTEC, the Department of Neurocognition at the University of Bielefeld. The story was that I gave a talk at Bielefeld, I guess 7 or 8 years ago, about a toolkit that we built for visual observation of users of mobile devices, cell phones and tablets, where we were measuring attention, fixation, emotion, etc. And afterwards, Schack came to me and asked, well, could we use that as an experimental tool for some of our work with neurocognition? And so we got our minds together and said, sure, why not? We wrote a proposal, and this is what came out of the research, and in particular, the doctoral thesis. Now, these are a few slides from a 40-minute talk, and I've got 10 minutes. It's 14:54 at 14:64, that is to say at 16:04. Todi is going to, Kashyap is going to interrupt me. So let me just say the paper can be found here on the chat. You can download the paper and read the paper that goes with this talk. And if there's any more questions, well, I'd be happy to talk about that. Between the 2 years where we submitted and wrote the proposal and where we actually got the grant and got started, the landscape of visual observation of emotions and fixation changed dramatically. For one thing, the doctoral student and the engineer who had built my tool had left, so it was no longer maintained. But even more importantly, a number of commercial products came out on the market that did much better than our homegrown lab tool. So we pivoted. We said, okay, well, instead of using our own tool, we'll do a competition between all the different things we can buy on the market, eye trackers, different techniques for looking at faces, posture, fixation, etc. And we built an instrument to observe chess players as they solve chess problems. Okay, these are chess players, intermediate or expert, ranked by their ELO scores. And what I'm going to show you are some of the things we discovered from that. Well, of course, we measured body posture, initially with a Connect, but more recently with Open Pose, which seemed to give us quite good results. We, of course, had several different techniques for measuring facial action coding, but it's not the Ekman basic emotions we're interested in. We're more interested in valence, arousal, and dominance, which I'll explain a little bit more about. And most importantly, we tried and tested several eye trackers that we mounted down on the bottom of the screen so that we could watch the attention and fixation of our chess players as they were solving problems. So, of course, we were able pretty rapidly to show that with a deep neural network, we could predict the next move just from fixation and attention for different players. Okay, that's fine, but it's a descriptive model. It doesn't really tell us why that move was made and what the player understood. And what we were really interested in is coming up with a cognitive model to explain how people reasoned about the problem and what visual observation of their body and face and other features, such as heart rate and things, could tell us about how they were reasoning, including, by the way, blink rate and pupil dilation, which we also made good use of, Zoya. That's absolutely something that's very important for concentration. So we did our first pilot study in March 2017, basically to verify the experimental equipment. We got together with a local chess club and laid out a set of 6 time-limited tasks of increasing difficulty, starting for things that were fairly simple for an intermediate player and ending up with 3 problems that were absolutely impossible for anybody. Okay, and we wanted to verify that eye gaze and emotion would correlate with expertise, and basically say if we could tell the expert players from the intermediate players just by how they reacted to the problems. We did 2 sessions. The first session, which was a lot about debugging the hardware, where we had 21 subjects, but only 14 usable recordings. And the second session with 9 subjects and 8 recordings that were usable. Remember, this was a pilot experiment. And from these 22 useful recordings, we had a very surprising result. Self-touching, rate of change of emotion state increased from a neutral during reactive play, when people were just basically playing an established opening, to frequent touching and rapid changes of emotion as they became more challenging, even for experts. We could see very rapid, frequently changing emotions on their face as they were reasoning about the problem, correlated with pupil dilation, among other things. Why? This didn't fit any established model. Okay, so it took us a while of exploring. Well, here's some of the data. The experts are in red here. This is the count of self-touches as the difficulty of the task increases. And on the right, the number of changes of emotion per second, okay, as the difficulty increases for intermediates and for experts. We left off the beginners here. And in particular, you can note in the last 2 problems, there's a complete drop-off. Okay, what happened? The problem was so impossible that the intermediates recognized they didn't know how to solve it and they gave up. And you could see that in the data. The stress level went down, their concentration went down. They said, oh, I'm nuts, I can't do this. What's going on? Why would emotions change rapidly as people were trying to solve problems? Well, to get deeper into that, we needed to look at the physiology of fixation and emotion. Of course, we know that the eye tracker is really a reflection of what's going on with the superior colliculus. This is the organ that controls fixation. It controls where your eyes go, gets inputs from different part of the brain, visual system, auditory system, etc. And it controls version, and cyclotorsion. So basically, this is getting stimulated from what you're looking at as you're looking at the chessboard. But more importantly, we're also interested in something called the lateral genetic nucleus. This is the filter for attention. The LGN suppresses non-attended visual information and relays attended information into many different regions of the brain. Okay? And the LGN really is this nucleus of attention that's happening as people are trying to solve problems. Well, to make that, for people who haven't thought about it, this is roughly what it would do to your perception of the chessboard. Okay, if you're attending to the queen, the white pawn, and the king, and maybe the black bishop, those parts stand out. You see them at the expense of all the other pieces. And that's pretty much necessary because the number of pieces and the number of configurations is way beyond what your working memory can handle. Okay, so really understanding working memory, not short-term memory, but working memory is a key component of all this. There's a classic paper by George Miller from the 50s, The Magic Number 7 ± 2, which explains limits on capacity for information processing. This is easily demonstrated in anybody's laboratory by having memorization experiments, have people memorize sequences of digits or images, sequences of images, that would work. And you can basically show that beyond 9, people can't, the short-term memory dies. You can basically demonstrate that there's this working memory with limited capacity, and it seems to be driving perception and action. And like I say to my students, perception is active and action is perceptive. You perceive with acting and you act with perceiving. These are directly driven by, or this at least our models believe that these are driven by working memory elements. And we wanted to show that. Well, what's working memory for? Working memory entities are really a kind of association station for association of perception and action with long-term memories, with episodes remembered from the past, with concepts, with procedural knowledges, with actions you can take, etc. Okay, and this is widely used and modeled in people like Kinch, who was trying to explain reading in his book Comprehension. So what we wanted to look at was this phenomena between working memory and long-term memory, and how that can explain these rapid changes of emotions that we see as people are trying to solve problems. Well, Anderson explains that the concepts go into long-term memory where they become associated and then come back as new entities putting into working memory. Okay, but how do you decide which of the multitude of entities go into working memory? How do you decide which of the multitude of concepts you use to understand your chess players? Well, to do that with Professor Schack and our doctoral students, we built a formal model for mental concepts using frame notation. Essentially, the chessboard gave us a nice formal environment that's very sterile, where we could formalize the pieces and their relations into chess chunks. And beginners, we could well establish just by observation, reason with individual pieces. They'll look at a pawn, they'll look at a bishop, they'll look at the king. Okay, and their working memory becomes immediately overloaded and they're completely lost and they don't know what to do. Experts reason with chunks. These are associations of pieces that have meaning. And an expert, an intermediate, learns a vocabulary of chunks from experience associated with episodes of memory. And when you see the chunk, you call back all the things that happened to you from those episodes. As people become more and more expert, as they gain more expertise, they learn more and more chunks. Gobe and Simon reasoned or argued that the typical expert has well over 10,000 chunks that he's reasoning. But how do you decide which chunks to apply to the board? Even with chunking, the expert is rapidly overloaded with different possible interpretations. How do you decide which interpretation is useful? Well, our hypothesis was that we could use emotion. And Kahneman has recently argued for just this reasoning, in his book on thinking fast and slow. Emotion gives us fast, predictable, reactive responses to a situation, whereas cognition is slow, deliberative, and creative. Okay, and our hypothesis became, working with Schack, that we could use emotions to predict which chunks people would come up. In particular, not the Ekman 6 spaces, but by converting that into pleasure, arousal, and dominance, we reasoned with our model that pleasure could be associated with the frequency of positive or negative outcomes that happened with a chunk, that arousal was associated with the imminence of opportunity or threat, and that dominance was associated with the confidence or ability to control the outcome. So by placing that into our model, we were able to formulate a second experiment where the emotion associated with parts could be well shown on mixed subjects. So we did a second experiment, this time associated with retroactive task explanation, where we got a history of the chunks that were done by the players. And what we found was indeed spikes in arousal, valence, pupil diameter, fear, and disgust corresponded to self-reported recognition of negative and positive concepts based on the chunk. Well, I've reached the end of my time. Okay, so this, of course, has limits. It was work in progress. It was a first cut to explain comprehension and prediction of behavior. And of course, chess is a much simpler domain than the real world, but it's a preliminary investigation that we think opens some concepts for further experimentation and opens a number of challenges, but also possible applications in things like teaching driving or educational cockpits. Okay, so I've taken 11 minutes. I promised Todi that I would stay within 15. So let me just say that there's a rich literature on this. You can find much of it in our paper, and I'd be happy to take questions. Albrecht or Todi?
Yeah, perfect, thanks.
Yeah, Kashyap. I think we take the questions, we collect them for the panel, that we get them directly. And so I think we would directly switch over to Robin.
Okay, very good.
And
thank you.
Make sure to get the questions into the chat, that we have them later, and then we can sort of, because I think there are hopefully things that link to each other. So hopefully we'll get there. And thank you for sort of you packed a lot into the 10 minutes. So it was really great. Thank you.
I told you that would happen.
So now it's the question, can you hear my, can you see my slides? I guess so, right?
Yes.
Great, okay. So today I'm going to talk about a different aspect of humane AI and memory, and namely the understanding of autobiographical memory in virtual reality. And we are doing a micro project right now that was motivated by this thinking with the DFKI, with the University of Auckland, and here the LMU Munich. So when it comes to AI and memory, the big question for me that came up is when there's more digital content coming into our lives and that is generated potentially by AI, how can we still know what is our memory that is from the physical realm or from the virtual? And how can such memories that are provided by digital content shape our personalities and ourselves? And this domain of memory is called autobiographical memory. And just to give you a little grasp on what autobiographical memory is, I'd like you to do a small experiment. So do you remember, for example, where you were on the September 11th of 2001 and what you ate that day and what you drank that day? I think a lot of people typically remember, and if you put that in the chat, then it becomes apparent, for example, that we all share that there is on these events we have certain memories that are totally emotionally relevant. And also turning to slightly more positive scenes. So what did you do on your 18th birthday? So I still remember that I got my driving license, for example, and I drove really slowly throughout the town with my car, and I was stopped by the police at that point, and because they thought I was a drunk driver because I was driving so slow. And I will never forget this specific event in my life, and I'll always remember the fear of the police of that day. And so in this domain of specific events that we have in our lives, there are certain events that we cannot forget. And these are called typically episodic memories that are experienced firsthand in a given context. For example, when I say, I saw an apple falling from a tree yesterday when I was outside, this is an episodic memory. And when I say, I remember my favorite coffee cup breaking yesterday when I stumbled across the kitchen floor, and this made me sad all day, this is a rather autobiographical memory because it entails self-reflection, emotional evaluation, and some semantic processing. So in this domain, where there are really self-relevant memories, we can ask the question, obviously, how outside of the physical realm, there's also the possibility that digital content can encode such autobiographical and personal memories. And we think that this is typically really interesting in the domain of virtual environments, whether they can encode something autobiographical that is interesting to ourselves. So researchers from the University of Osnabrück did an attempt to quantify that. They mainly provided a cinematic VR video to one group of people and a simple desktop video to another group of people and let them experience that. 2 days after, the subjects had to come to the lab again and had to categorize new and old pictures of such a scene. And what they could show is that retrieval success was better in such a virtual environment, and also that retrieval took participants a little bit longer. So it appears that virtual reality encounters can be encoded in long-term memory, quite like autobiographical memories really deeply. However, to get a good grasp on autobiographical memory within virtual environments, the question obviously comes up how this relates to physiological signals. So we have distinct pattern in memory when encoding and when retrieving memories, and we can see that in brain potentials, typically in the EEG. And now the question arises whether VR memories and, let's say, lab memories or real memories, depending on the view, whether they have the same physiological potentials when being retrieved. And Kiska, Gruber, and Schöne did a study on exactly that, comparing the physiological signals when recalling autobiographical memories from desktop versus VR. And they could show that there is a slight old-new effect on the delta in the EEG. So brain potentials mirrored that of what you typically see in lab experiments on autobiographical memory. However, they had slightly mixed results because it was really taxing for them to get subjects into the lab for a long retention interval for a few days. And I think there's a lot of research to come in this area. So what interested us in the micro project is something different, namely to see how autobiographical encoding and recall works in the VR. And therefore, whether we can detect autobiographical recall within the virtual environment, not outside. And so we teamed up with researchers from the University of Auckland. I think Kunal Gupta is in the call as well, to create virtual environments that can elicit such positive and negative emotions relevant for autobiographical memory, and get encoding as well as recall done in such environments, and measure EEG while doing that. And from this, we will, in a couple of months, hopefully have a labeled EEG data set on which we can train models to detect autobiographical recall within the virtual environment. And from this, we hope to get a better understanding first on autobiographical memory, a way of quantifying the emotional experience in VR using AI, and also to get a first proof of concept how it would be possible to adapt a virtual environment with regard to self-relevance and autobiographical memory. And with this, I'm happy that I'm a little bit done a little bit earlier with the talk. And with this, I would just want to spark interest in the field of autobiographical memory and detection and physiological sensing within VR, and hope that we can spark some nice micro projects in that area.
Thank you, and I think nobody is complaining about being faster at this point. Here too, we keep the questions for the panel. And so perhaps we can go to the next speaker. Have you already sort of, can you, I just have to check.
I think, yeah, I think I should be the next speaker. I don't know.
Yeah,
but
so I was busy. I lost the window with my schedule, so I was sort of a bit surprised. But I think you are the next person. And worst case, we have swapped the last two, which is, I think, given that we are a bit over time anyway. So Catharine is talking about memory-aware conversational agents, and
yes.
so
Give me one
where
second.
is the
Yes, I think I should share now. Let me see whether it works. Can you see my screen?
Yes.
And you can hear me? Perfect.
Yes. Yes.
Okay, great. Okay. Very nice to meet everybody. My name is Catharine Oertel. I'm an assistant professor at TU Delft. And I am giving a talk for Catharine Jonker, who is on holidays this week, also enjoying. I'm not sure about cross-country skiing, but something along those lines too. My talk is a little bit going away from vision, which a lot of people have focused on, more to conversation and how memory relates to this. And a bit different from other people's talk too, is something we are in the process of starting and we would like to start further. So it's really not finished research yet, but yeah, let me try to give you the general gist of it. So the goal of this micro project we are proposing is that we would like to investigate how human recollection of team meetings is and how conversational AI could use this information to create better team cohesion in virtual settings, such as now, basically. So we all been working in hybrid settings. We've all been using Zoom all the time, and like we just had the problem with me sharing my screen or like finding eye contact, etc. So how does this really affect what you take out of a meeting, and does it affect it at all? We did some initial pilot studies, and what we found is that actually people take out different things out of a team meeting. So maybe you remember the point you already went into, the point you wanted to stress, or maybe it's related to your social role in the meeting. If you're a moderator, maybe you remember more, you recollect more of what was related to this. Whereas if you had a fight, maybe you remember that. So it seems to be quite variant, and people don't all remember the same thing. So what kind of methodologies do we want to apply, or what have we applied in similar projects? The general idea is that we want to use sensory information. So by sensory information, I mean basically information from the face, automatically extracted speech. So speech also meaning the speech melody, how your intonation is, how engaged you sound, and eye gaze as well. And then we would like to just collect a lot of data in order to model it, and to model it to a higher level construct. So if I was talking about a team meeting and like what you take out of it, one higher level construct, which might be quite interesting here, is the level of cohesion. So how does this also affect how well you're getting along, or how much you think you're a cohesive unit? Yeah, so that's basically what we would like to do. And what have we done in the past, which is related to this? So one larger study we've done was concerned with the D64 corpus. The D64 corpus was one of the first corpora which was recorded in the wild, as far as you could get back then in 2012. Recording in the wild means that it wasn't in the lab, it wasn't recorded in the lab, it wasn't scripted, or it wasn't really task directed, but it was basically 5 people in a room equipped with a huge array of sensors. So you see the weird bubbles on people's hands, and these are motion trackers. There's like microphones everywhere, there's video cameras, etc. And of course, such a corpus has some problems, because in 5 days, people go up and they might start a water catcher, right? And anyone who has worked with extracting information from sensors knows that that will probably heavily impact your speech recognition occlusions from video cameras. So we looked at this, and we found there seems to be a lot going on in terms of engagement, and that was also related to difference in age, gender, and social background. Now, why is engagement related? So the first hypothesis we had that engagement also really influences what you're remembering, what you're memorizing out of a meeting. But as any, or as most of these concepts, it's quite fuzzy. So there is, if you look into the literature, there's a huge array of different definitions of what engagement is, or what it can mean also for human-robot interaction. How we defined it in this study was basically we wanted to capture the degree of perceived interest of the individual, but also as a group of a whole, which was quite novel at this point in time. And different from other definitions, we really wanted to look also at the affective component of what it means to be engaged. Like many of you are as well, we looked at eye tracking as well. The only difference is that we didn't look at it as a screen, but we wanted to look at it in a 3D space. So as a first approach, we had to actually annotate it manually because there wasn't, at this point in time, there weren't any sensors available which would allow you to do 3D tracking. But what we found is that eye gaze was actually a great cue in order to automatically predict the degree of engagement of a group and of the individual. So we looked at, for example, the symmetry, so the amount of mutual gaze in an 8x8 matrix. So if there's 8 participants, 8 times 8, or also the amount of maximum gaze on one person, entropy and presence. This could led us to predict the amount of engagement to a high degree. Then for anyone who has manually annotated eye gaze before, they know it's quite soul crushing if you have to go frame by frame and try to see where someone is looking. So we collaborated with Idia from Switzerland, and we looked on how to automate this. I hope this is playing, but basically we use Kinect data, in order to be able to automatically see where someone is looking in a 3D scene. Different from glasses, Tobii glasses, for example, which are nowadays available, it's less intrusive. So you don't get a headache of it wearing it for longer periods of time, which was quite nice. So, but as you gather, that's why I'm also here. It doesn't really tell us that much about memory yet. So that's really what we want to explore. We have our hypotheses about engagement. We have our hypotheses about entrainment. So how much people prosodically entrain to one another in a meeting and how this is related to memory. And we have first findings, but really what it's needed is that we have a larger scale longitudinal corpus where we look also at personality, at social role, emotion, or affect, and how this is all affecting the recollection of team meetings. Crowdsourcing tools, we also looked at different ways, not only to label data from images, but also to how to make it interactive so that you have a context to it as well, an interactive context through dialogue systems. And I know I'm running out of time, so I'm going to be really quick. This is in also in relation to a larger scale project, which is funded by our university as well, where we're looking also how to get a social robot to interact with people, remembering over longer periods of time, remembering episodic memory, as someone was referring to in the last talk. Okay, I hope now it was relatively quick, I hope.
Thank you so much. And also here, please put the questions into the chat that we have them later. And just, I'm really looking forward to the discussions because there are so many things that also interlink. And now we have the final talk. And so this should be Aurélien. Also perfect, already there. So another 10 minutes and then we are in the panel session. And so make sure you have your questions ready and put them in the chat so we can really get this started on.
Hey, yeah, so I'm Aurélien. Thank you for having me here. I will talk today about recent submissions that we did for IUI 2021. So with several people here in Aalto University. So the starting point of this project was the self-teaching application. So there is a lot of self-teaching applications and they are very widely used today. So for instance, Duolingo counts something like 100 million plus downloads on Google Play. We can imagine that these applications play the roles of artificial teachers. So for each interaction with the user, they have to make decisions regarding which teaching material to present to the user, alternating between presenting new items, like here, and after that, presenting a review. What is interesting is the algorithm behind these applications is most of the time a rule-based algorithm, and most of the time it's some variation of a Leitner system. So the intuition behind a Leitner system is very basic and straightforward. Is if the user make an error, you increase the frequency of review of the item, and if user is making a success, you decrease the frequency of review. So the advantage of this system is that it's very robust, it's not expensive computationally, it's fully online, and it adapts to some extent to each user performance. So our goal for this project was to consider a model-based alternative where the user's memory state is inferred while interacting with the user and selecting the optimal item to present based on this inference. So to do that, we formulate the problem as a sequential decision-making problem, namely a partially observable Markov event decision process, aka POMDP. So in a classic POMDP, the elements it presents are the actions an agent can do, the states the environment can be in, and the reward the agents received. And in case of a POMDP, so which is partially observable, you also have transition function that indicates how you move from one state to another. So here we consider that the agent is a teacher and that the environment is a learner. The actions are the possible items to present, and the states are the memory of the learner, the memory state of the learner. And the rewards are basically the degree of knowledge of the learner. So to solve this POMDP, we separate the problem in two parts. So inference, handled by the psychologist component that infers the learner states and make predictions. And second, the planning, which is handled by the planner, whose goal is to use the predictions to find the best item to present based on some learning objective. So for processing with the inference, for dealing with inference, we need to define two things. The first thing that we need to define is the probability of recall. So we need to have a model for that. Here we consider a very simple model. We assume that the memories were forgotten with an exponential decay according to four things. So the number of repetitions, the times elapsed since the last repetition, which are things which are known from an external observer, and that it was also a function of a repetition effect. So how the forgetting will decrease when you repeat, when you review an item, and the initial forgetting. So how basically how fast is an item is forgotten after an initial presentation. So basically, it looks a little bit like the graph that you have on the right, right? You have a first presentation, and after the review, the forgetting decrease. So things that I didn't say is that this repetition in effect and this initial forgetting are latent variables. They are unknown, so we need to infer them. So they are basically the parameters of our model. Second thing then that we need to define to be able to do an inference is how to revise the belief over the parameters after a new observation. Here we make a very simple also assumption. We just apply a Bayes rule. So we basically compute the posterior over the parameter space. So for the planning side now, what do we need to define in order for our system to work is a reward, first of all. So once again, we take a fairly simple definition here. We consider that the reward was the number of items learned at the time of the exam. And we also, at this point, need a definition of learn, and we consider that it was the fact that the probability of recall of the item was above some threshold, for instance, 90%. And good thing is that the probability of recall is exactly what provides the psychologists, Second thing that we needed to define is how to choose an item. So here we considered two possibilities. Solution one, which is a very straightforward solution. We call it myopic planning. So here is basically if an item which has been presented fall, the probability of recall of an item which has been presented fall under the threshold, then you present this item. If all the items that you saw before are above this threshold, then you present a new one. After that, we consider second type of second solution, the second type of planning, which we name the conservative planning. And here it's a little bit of refinement of the myopic teacher. Before presenting an item, he will check that he will do rollout, so like simulations until the end, and we'll see if all the items that have been presented are able to be remembered. If not, he will decrease the total number of items to present to the user, such that all the items are correctly recalled in the end. And finally, for testing the efficiency of our system, we test it with artificial learners first. So we use the same conditions the ones that we use for our human learners. So namely 1 week of training plus 1 exam in the end. To evaluate the quality of the planning, we consider at first that the psychologist knew everything from the learner. So it's the first row here. We look at how bad or good our myopic teacher and conservative sampling teacher were doing then. What we observe is that the total number of items was on average higher than when using a Leitner system, which was our baseline here. We also looked at We also look at the number of items learned, the ratio between item learned and item seen. That was an indicator of the precision. And there, the myopic teacher was doing less good than the baseline. And the conservative sampling was behaving perfectly by definition, actually. After this first preliminary results, we assume that the psychologist didn't know everything. And so we release the assumption of an omniscient psychologist. We can see here that the error of prediction is diminishing over time, meaning that the psychologist was actually able to learn something from the user. Regarding the results, so the pattern was similar regarding the baseline, even if the comparative advantage was less important, especially for the conservative sampling teacher. And finally, we tested with human, so with 53 human subjects that were having 2 training sessions per day for 1 week. So one with a rule-based system and one with a version of our system, so ever myopic for some subjects, ever conservative sampling from some others. So good news is that both versions of our system are doing at least as well as the baseline. But the bad news is that the number of items learned is not greater when using the conservative sampling, which were our best candidate. However, looking at the precision, so here, we can see that both the Leitner and the conservative sampling had similar performances, while the myopic is significantly lower. The same to this regard to what happens during the simulation with artificial learners. Also, to check that our system actually adapts, we look at the best guess at the psychologist at the end of the task. You can see here at the bottom the distribution of the parameter values depending on if, depending on if you do the average over all items to have an ID for each user. So you have 53 points here. And here, the contrary, you're doing the average over all the users. So you have an ID for each item. There were around like 2,000 different items. So there's a lot of possible future for this work, where we were mainly aiming to create a framework to build upon, actually. Obviously, we could use a more sophisticated memory model. We take a fairly simple one, and also improve our sampling algorithm. Other thing is we would like to model explicitly the similarities between the individuals, so between the users and the items, what is actually to have a hierarchical approach instead of estimating everything separately. Another possibility will be to try to model the interaction between the items. So for instance, if you learn cat, does it help or interfere to remember dog because of the semantic relationship between the two words? And finally, we suppose here that the reward was the same for each learner, doing great at the exam. However, the learner goals can be very different depending on each learner. It would be nice to integrate for the future something a little bit more flexible to this regard.
Hey, thank you.
Yeah, you're welcome.
And thank you for a great presentation. Also, thank you all speakers for the presentations. And without any further, we move directly to the panel. And I think we get started with the question we stacked from Kunal after the keynote, and then we'll look through the chat to see what are the other questions and how many we can fit in. We have another 20 minutes because I think sort of we don't need much for saying goodbye. And I think so. Kunal, are you still around? Can you put a question? Oh yeah, perfect. So please put the question.
Yeah. Yeah, thanks for the amazing workshop and all the talks. So my question is from Zoya. Like you mentioned about memorability in your talk, and so did you study the emotional versus neutral images in terms of ability? And if you did any interesting insight or anecdote from that study while recalling?
Hi, thanks. I didn't specifically, but there has been a number of follow-up work looking at emotion and the emotional kind of valence of the images. This was done with natural images, and actually the face project that I showed you, the face memorability project, did look at the emotional content of the images and how that affects memorability. Interestingly, across multiple studies, well, the basic answer is yes, emotion affects memorability. Interestingly, negative emotion affects memorability more. So say peaceful and calm scenes and faces aren't as best remembered as a more negative, maybe scary or aggressive or scared faces, and then emotional stimuli that are supposed to evoke emotions. So maybe scenes of violence. Hopefully there's not too many of them in this large memorability data set, but there are some that imply some negative events. And I think that it also boils down to this utility of information, this working theory we have in the group that if it's going to be useful to you, you will remember it. And it's related to these episodic memories that were discussed here as well. That once your emotional centers kick in, there's more wiring happening, right? Not more wiring, but more activity happening in the brain to help consolidate those memories. So indeed, emotions are related. If you're interested in particular papers, I can also send them to you, linking the two.
And I think James had also one comment to it. So James, can you unmute yourself?
I don't think I need to say it. I wrote it. Arousal correlates with recall. Yeah, it's well known. But Zoya, yeah, absolutely. And if a scene arouses a menu, if a scene invokes an arousal, it makes you excited, then yeah, it's more likely that you'll remember the scene. But what is it about the scene that invokes, that evokes arousal? What is it about the scene that does that? That's the interesting question.
Okay.
Thank you.
And there's another question. I think, Kunal, do you have a response? Sorry.
I was, James cleared that because my next follow-up question was about the arousal dimension and the memorability and recall. But yeah, thank you very much for the response.
I will add something. This isn't something we did specific research on, but it was a qualitative observation in some of my eye tracking studies as well, looking more at attention. In answer to what is it in a scene that evokes arousal, sometimes it's not content in the scene, but it's content that you project onto the scene when you play it out in your head. So there's many people that subscribe to the view that thinking is simulation. You're simulating a few moments ahead before they happen. And so when we look at images, we're doing the same thing. And there could be images that to a computer, currently trained artificial system, it looks quite normal. Maybe there's a ball flying through the sky, but you are playing it forward and you know where this ball is going to end up. And that could cause arousal because you realize, oh, wait, this is going in a very bad place. And you can play out what that scenario will be. And so we see in eye movement in our eye tracking studies that people's attention goes to where the future state of the image will be. And that's not something that we can predict using AI for now. That requires a lot of context and future planning. And I think similarly for memory, some images that maybe don't have inherently memorable features, those images are being played out in your head to their memorable futures, and they can be memorable for those reasons as well.
Yep, absolutely.
I think there is one thing which comes to mind. I think this also, what is memorable may change massively. I think there have been now experiments on the pictures we would have found memorable 10 years ago and now omnipresent on Instagram. Like these reflections, like yourself in front of a lake, of a mountain, whatever. So I think it's quite an interesting thing that is just maybe also something that's massively changing over time. And I think we have one more. Jean-Paul had one. Can you unmute yourself?
Yes, hello, thank you. I think my question links with what Albrecht just brought up. My question was that if you have a data set containing highly memorable images and some lower memorability images versus the data set containing only the lower memorability images, my question was whether you observed that the higher memorability images actually decrease the ability of people to remember the lower memorability images, because you sort of get exposed to these much more interesting images, if we can put it like that. And so is there a danger perhaps that, like we see with what Albrecht mentioned, all these pictures that are now commonplace, users become desensitized to high memorability images, and whatever optimum you get is not stable in your model?
So what's a memorable image is going to change over time. I talked about it being intrinsic, but I think the way to think about it is intrinsic given the average context that we can imagine. So it's intrinsic to maybe the images that people have been exposed to up until now across our US crowdsourced population. So that's the long disclaimer there. But that means that as our experience evolves, as the images we're exposed to evolves, what stands out, again, right, pulling in from classic psychology and some of the things I talked about, what's going to be distinct to you will change over time. What's not going to change is that what's distinct to you will be most memorable. But exactly what that is will change. And so that will explain that, if we keep seeing the same images over and over again, yes, they're going to be kind of compressed in our memory. They're going to fit this template. We're going to remember the template. And maybe what we're going to encode is the differentials, right? The differences. We're going to remember the images that differ from the template most. But what that template is, it's a moving target. In terms of saturation, we do see that as you increase the diversity of the images in a set, so you combine a whole lot of really different memorable images together, you can, in the exact same period of time, have people remember more. So if I showed you 100 airplane cockpits versus 100 images from different scene categories, you'll actually do much better on a recall task if you see those different images. There's going to be a saturation effect. A memory will increase up until some point, and then you can't remember that much more. But there's earlier studies in psych by Talia Conkle and Tim Brady from Oertel's lab showing like the remarkable capacity, and the paper is titled something like that as well, the remarkable capacity of memory and the details that you can encode for objects. So you can somehow, without having a snapshot picture of every image, you are able to say whether or not you've seen thousands of objects and images before, which is pretty cool.
Thank you very much. I think for me, the most interesting part was trying to think in terms of the data visualization examples that you brought up. If we all start trying to exploit high memorability data visualizations, we end up in a situation sort of back where we started. If all visualizations are interesting, none are.
Well, they can be interesting in different ways, right? It's not just about high memorability making them more homogeneous somehow. They'll be high memorable if they're different from each other. So as long as you optimize for difference, then I think you'll be fine.
That's an interesting approach. Thank you very much.
Thank you.
Going through the list, I think Wendy had more like a comment, but I'm not sure if you want to extend it. If you're still around, I'm not sure.
I'm here, but I didn't really have a question. It was really just more of a comment. So I think it's fine. But it's a fascinating talk. It's really great. Thank you very much.
And then Phil had the question just now in the Phil, would you? You don't have a mic. So, okay, no worries. So we'll read it out. Is there research that shows what is memorable for people with memory disorders such as dementia? Would this inform how memory is modeled? I think a very psychology-heavy question. Who wants to jump in?
So just maybe from a psychological perspective, as a trained psychologist, so there is a lot of research that can show, for example, in the domain of stroke patients that have lesions in certain brain areas, how memory unfolds, of course. But I'm unsure, maybe Zoya knows better in the domain of memorability of certain features. So apparently I'm not familiar with like features of pictures, for example. So on the short-term side, that'd be really interesting, I guess, but also highly problematic to sample, because typically we need for this memorability research, I guess, a lot of trials, right? And these patients are rare in a sense, and so we lend to have more to have less trial heavy stuff going on with these kind of patients.
I think there's the question somebody put in the chat, will this go onto YouTube? Yes, we will. We have a recording and this will be online. And somebody else mentions, Phil mentions the IRB proposal sort of going into the ethics committee is probably quite tricky.
Can you remind us what IRB means?
Institutional Review Board, it's the ethics committee in a US institution.
All right. I would be surprised if you put this on YouTube. I thought we had a server for Humane AI that would be more appropriate.
Yeah, I'm not sure where it really goes, but it will be publicly available to people who. So I think yeah,
sorry.
Please.
I had a question that built upon the previous one about specific people. This might be for everyone. So I was wondering about how individual differences have impact on results, be it for predicting memorability or detecting autobiographical memories, or for language learning for all the other applications. So I'm just wondering how much you've looked at this, each of you, and if you've seen that you can kind of consider people more or less homogeneous in set of people at least, or distinct differences really kind of impact the results.
Yeah, I can maybe go on this actually, because it was one question that's arise in the project. So in the context of learning, I will not pronounce myself for the other context that I don't know much, but in our context, it shows that there is some kind of variability, actually, not only at the user level, but also at the item level. So that's why we try to model that. So for now, we did it in a very naive way, because we consider that everything was independent. In the future, we will try to actually model how actually distributes over the population. So population of learners and population of items. So assuming that there is a parent distribution. But yeah, assuming that everything is the same can be a working hypothesis that can make the things simple at first. Actually, I didn't present that here, but we had like a preliminary results with artificial learner when we assume that it was the same for each learner. But yeah, at least in a teaching context, I think we can expect a high difference. And I think it's also, okay, something to not forget, let's say. There is a series of publications about intelligent tutoring system, which are assuming actually like some kind of like ground truth for all people, all items, like everything is the same. Or sometimes it's only the items are different, but every learner is the same. I think we should try to get rid of this kind of working hypothesis as soon as possible. Yeah.
Thanks.
More questions? I think Trash has another one. Do you want to put it directly or should I read it out? Okay, so I read it out. So can you elaborate on Nemann's approach to measuring forgetting rates for both types of forgettable and memorable?
Let me try to make sure I understand the question. Is this Newman like is this the video memorability work that I was referring to?
No, I think this approach from 2015, I think it's a paper. So the name of the author, if I'm writing his name correctly.
Is this something I presented or not?
Yes, yes. So it's about forgetting rates for forgettable images or like features. So the forgettable rate for.
You're like, asking about like the curves of decay.
Yeah, exactly. How did he measure the rate and about his approach for measuring the forgetting rate for both images? And yeah, does this approach like go for both type of images? So or only for this forgettable images?
No, yes. So Annelies Newman is the first author on a video memorability project from 2020. So it's a project called Memento. I'll see if I can find the link. It was an MIT project on video memorability where they captured the memorability scores of 10,000 videos. And in order to study how memories decay over time, what they did, they reused this paradigm of like a sequence of videos, just like a sequence of images. You're watching this like infinite movie of 3-second video clips. And some of those videos will repeat later in the sequence. And if you vary the time between the first and the second presentation of a video, of its repeat, so maybe you show something 10 videos later, 100 videos later, you can capture a few points along the curve. And you can do this for every video. So different people will see the same video replayed different amounts of videos later. And then that gives us a point on the curve. And if you capture enough of those points, you can build up this whole curve and you can fit a line of best fit to it. So usually the working hypothesis is that memory decays using a log curve, a log function. But actually what they found with videos, at least at the lags that they tried, at the delays they tried, they found that a linear fit was best. And that made it to some extent easier for them, because then they could just predict the slope and a single value on the memorability curve. And they trained a deep model to take as input video, like the 3-second video, the visual features, optical flow, and then to predict a score and also a slope. Does that answer your question?
Yeah, a bit, thank you.
If you have more follow-up, either type it or
yeah, I just was wondering about, like, did he like develop any KPIs for forgettability or memorability, and then you have a unit for this, and then he measured this unit as a rate? And when we talk about rate, I always imagine that something like over time, and what this unit per time, and what this curve is gonna look like.
So this is for memorable and forgettable images. We're measuring the decay the same way, but we do see different decays for different types of images, different types of videos. So the memorable videos have a shallower slope than the forgettable videos, but they're tested the exact same way. You just space the repeats apart differently, and then you measure the curve. And at prediction time, you end up accurately predicting different slopes that decay over time.
Yeah, I got it. Thank you very much. I also may need to read the paper. Thank you very much.
Okay, so I think with this, we are spot on. It's 4 o'clock in our time zone, and whatever your time zone is. But I really enjoyed the discussion. I think, as we hinted, this may be the first of several workshops. I think we feel the time is too short to get into depth, but I think it is really what we've seen from the presentation. It's an extremely important topic. I think human memory is a lot what makes us human, that we can remember things. And so I think understanding this, and I think we have seen very different views. So I feel like sort of James may have introduced the Petri dish with the chessboard. A Petri dish we can study certain things on, and I think also the ideas that applications may come out if we get sort of to a better level, as Zoya said at the beginning. I think that's really exciting. So thank you again to all of you who presented, and I hope I see you in another time. And please, if you have feedback, email us, let us know, and hopefully, we'll continue this discussion, and more is coming out. So till next time.
Bye-bye.
Goodbye.
Thank you.
Thank you, everyone.
Thanks, everyone. Bye.
Thank you, everyone. Bye-bye.